So today, uh, first of all, did anyone try the week 9.m2 stuff as far as trying to figure out primary decompositions of those ideals that we talked about? Oh, no eye contact. I like that. Okay, no problem. We'll do that in class today. Okay. But maybe we'll start it a little as a group and then let you continue it. So today we're going to do more of the first thing is the zero-dimensional primary decomposition, which we have gone through the entire algorithm now, I believe. Okay, so then we need to spend some time going through the full dimensional, I mean the arbitrary case. When I say arbitrary, we're still in the case where we have I is contained in K of x1 to xn. And we want radical of I, the minimal and associate minimal primes of I, and the associated primes, but also then a primary decomposition, which so we have four kinds of things we want. In reality, you could want other ways of packaging this data too, but anyway, this is good for now. We're going to talk about this a bit. Then we're going to actually spend a bunch of time on Macaulay 2, writing packages. Or writing. And I have two different examples I'm thinking of. One of them is just to make a very simple package that creates those ideals that we did last time, the oscillator ideals. So as something, and then I wanted to maybe do a more involved one, not that involved, but more of the kind of thing that if you're actually working on trying to understand something, how you might work on it, and that would maybe start with taking some of the functions in that week 9.m2 file, making a package of it, testing it, and then seeing how it goes. Okay. So anyway, that, and then well, I'd really like to do the full primary full case, not the zero-dimensional case, NEI inside of this situation. One other thing I want to do, which I don't think we'll do today, but is that there's a really cool, so today and some next time maybe, that there's a really cool relationship between associated primes of I and X, which is kind of wild, okay? I mean, that there is anything having to do with this. If you think about the algorithm we've done so far, how do you get the well, for zero-dimensional, it's not so bad. Remember, we just take these univariate polynomials, we factor them, we throw them in, and then if we are kind of lucky enough, we don't have to change coordinates, and or if we do, we have the normal position stuff, and therefore we can get this easily. We already did that one. That's the Seidenberg result, and then the minimal primes. That would be just ignoring all powers of all these polynomials we get, and then the primary decomposition is when we don't ignore it. So for this case, it's all pretty much the same, whether you do one or the other. However, in the full case, it is much harder to get this than to get these things. Happily, these are what you really want most of the time, but still, sometimes you need more, and so we'll also discuss that. And then, what happens is that the associated primes are what's hard to get. You can get the minimal ones in the list, but how do you get all the others? Well, if you're lucky, you can find an element such that when you do that annihilator or that element or that colon ideal, you find a prime, and then you know it's associated. That happened when we were doing the Alexander dual and primary decomposition of monomial ideals. We could actually write down elements that gave us all those minimal primes. But in general, that's hard. But it turns out that using X bubbles it to the surface. So it's actually very cool somehow. You can, even though these seem to be embedded, they're deeply somewhere in there. How do you ever find them? And somehow with these bubbles to the surface. So that is something I would really like to mention. So I figure that we want to do, right now, we're going to play with these zero-dimensional ideals. So Do you recall the algorithm for the zero-dimensional case, or should we just sort of spend a couple minutes sort of like reminding ourselves about it? Repetition, yeah. So does that sound like a reasonable plan? Okay, so here's the situation. So situation. We have R is K of x1 to xn. We're going to assume K is perfect. But there is a paper that which I can show you. We are not going to be doing that now as a project. That's fine. But where you can avoid the perfect case. Okay. In other words, if you need inseparable extensions or something like that, you can deal with it. But in fact, that's not implemented in Macaulay 2 so well. It isn't. It is a bit, but not completely. And now here we have I is contained in R, and this is zero-dimensional. And remember that that means that i.e. R mod I has finite dimension as a vector space over K. Okay. And then we went through, there's the number of points that you can get from that and so on and so forth. But what we knew is that we had the following polynomials. We have f sub I of xi is in I, but it's also in K of xi. Okay. So we have this thing, and this is a non-zero polynomial. If it's zero-dimensional, these have to exist. Okay. So we have these things for I equals 1 to n. So the idea is A, once you have, and you can tell it's zero-dimensional. How do you tell that? You compute any Gröbner basis and see that you have powers of all the variables as lead terms. Okay, so you can actually tell if you're in this situation. These things you can either compute using a Gröbner basis by eliminating all the other variables, or by doing some vector space arithmetic in here. Okay, so finding a linear dependence on 1 xi squared and so on and so forth. Now, so how does the algorithm work then? Well, the first thing is we had the square root of fi was equal to the square free part. You could get this by taking the GCD of that polynomial and its derivative, and then taking this polynomial and dividing by that. That gave you the square free part. You can also just factor it and see which ones occur to level 1. The kinds of stuff we're doing, the factorizations are not usually the bottleneck, so we don't worry about that so much. This really requires that K is separable. If it's K is perfect. If it's not perfect, then you have to do something a little different here. Okay, but there is something you can do. Anyway, we get this thing, and let's suppose that this is equal to actually, let's suppose that fi is equal to p1 to the m1, pr to the mr, and the pi are distinct, irreducible. I'm not going to rewrite that down. Okay, so this is a complete factorization. It's in one variable over whatever k is. And we'll assume maybe everything's monic. So assume all is monic. That way you don't have to worry about the coefficient out front, and everything's just unique up to order. Okay, so we have that. And then, well, in this case, the radical of fi is just p1 to pr. So the radical of this polynomial. And then the first algorithm that we had was that the radical of I was equal to I plus the square root of each one of these not the square root, the square free part of each one of these things. So this is square, I call it square root, but it's just the square free part of f1 to the radical of fn. Okay, that's only true if it's perfect, and we have to do something to change it. So this is actually quite nice that we can get this with no extra effort. Okay. Yep.
Wait, so this is a second step within step A?
That's step B. Okay. No, this is, we typically want to get these, we don't need to get them all at once. We have lots of options. We can choose one of the variables and calculate it and then worry about the other ones later. Again, in the kinds of things, even harder things, it tends not to be a problem, but until you play around with it, you don't really know which things are the problem. Okay, anyway, that's that one. Now, how do we get, so the next thing we can do is we can use the splitting thing. We can split I. So if we have f of, I don't care, any one of these univariate polynomials, okay? So if f of xi is in I, intersect k of xi. I'm just going to get rid of the f sub I now because we're just looking at one of them, okay? If f of xi is in here and f is equal to f1 to the p1 to, sorry, is equal, we factor it, we get p1 to the m1 to pr to the mr, just like over here. So we've done that already probably from part A, but what does the splitting go like? I is equal to I plus p1 to the m1 intersect dot 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 intersect I plus pr to the mr. Okay. And that's mostly because these are co-prime. In other words, if I take any two of them, they generate the entire ring. And we had a splitting thing that told us that if I have two of them, I could split it. And then basically that allows us to split the whole list of them. Okay. So this is actually something you can just check. And now these things are not prime unless these are 1. And even then, they're probably not prime because we've only factored one of these polynomials. But still, it's a pretty good bet. It's a pretty good simplification a lot of times. Also, in part C, the splitting of I, if we're only interested in the radical of I, this is equal to the radical of I plus P1. I mean, any time I have I as an intersection of primes, the radical of this is going to equal the intersection of all the radicals of these things. So there's not much going on here, but it's still a useful fact. So this is P to the R. Now, this is typically what we would want to do right off the bat, but we could do this as well. Because we want to identify what the primes are, and then we can sort of go back and do this part if we need to. So in part, the reason we need to do this is how do we tell if something is prime? Okay, that's actually really the crucial point of all this. Once we know that we have an actual prime ideal, then we know what the p's are, and then we can just throw in the correct pi's, and everything's going to be happy. Okay, but how do we know if something is prime? So anyway, we now have this all here. By the way, could any of these be the unit ideal? Better not be, because if it was, remember we have this fi is in there. I mean, anyway, we can take a look at that. But basically, if I do this on one of them, I get that. Now, if I factor all of them and I just add in one from each one, and I have R factors here, and I have a whole bunch of other factors for the second one, and so on, I can pick and choose, take one from each one, and that's like doing this, taking sort of one of these and then one other, and so on. Except that oftentimes those will be the unit ideal. So oftentimes what you want to do here is just do it by one of them, and then afterwards you take each of these and figure out what the polynomials are, and then do that. There will be things along these lines. They're going to be factored. These will be in there, but you might have a smaller thing. Yep.
I'm a little bit caught up on something from earlier.
Yes.
How many of these fi xi's in I intersect k of xi do we have?
We have one for each variable, x1 up to xn.
Got it. Thank you.
Okay. So and actually, to tell you the truth, we could do other things. It's all true. We could put it I intersect k of any single element that we want, but we don't need to do that generally. That's the normalization step. So then part D is we can assume now, if we're looking at if we're doing, okay, so now we want to find the minimal primes. We may assume in this setting, we have to think about the way it goes. Do you have questions, or is it, no? Okay.
Where did the exponents go in your radical?
Because if I take this, what's the radical of this? Well, if P1 of the M1 is in it, then P1 is in the radical. So the radical gets stripped down here.
Yeah,
For the radical.
distributes over acceptance, but I guess just the
So it's the radical of this, but the radical of this is the same thing as the radical of I plus, you can ignore the power. I mean, you might find other powers in here then, so you're not done. Okay, but at any rate, that's that. So you can think of this as a tree. But so what we might have, so for finding, I'm going to finish this off. For finding the radical of I, we're going to have the radical of I is going to be the intersection of the radical of I. I'm just going to say comma P1. And the radical of I comma PR, okay? And so the intersection of all these is the radical. And the first step is to find the minimal primes. Actually, the minimal primes and the associated primes are the same thing, right? So for zero dimensional, because they're all maximal ideals. There's no room for an embedded primes above it. Now, each one of these things, you can do the same thing. This is on using some specific variable. And actually, if you use the same variable, you're going to get just P1 again. It's irreducible now. So there's no way that's going to help you out. But you can choose another variable, and you can get this as an intersection of a bunch of radicals of some other univariate polynomial, and this one too. And then you get a tree. And then at the very bottom, what do you get? You have the radical of I is equal to the intersection of lots of ideals, let's say I sub j's, such that I sub j intersect each k of each variable is equal to is generated by an irreducible polynomial. In other words, we've totally factored each one of these univariates essentially, and we've got a whole list of ideals ij, which are the leaves of this tree. And now we have to figure out how to do that. So this is assuming that each f sub I of xi is irreducible. So that means that the ideal is radical, but it might still be the intersection of more primes. We just haven't detected that yet. And geometrically, this happens because this is really a projection onto something. So it could happen that when you project to all the different variables, you always have 2 points that you're never able to differentiate from each other. But it doesn't happen very often, actually, but it does happen. So how do we handle this? So here, we change variables to place, let's call, this is I now, is just one of these things, okay? So here we change variables to make, and wait, let's say what it is. We have to just find a variable that where all the coordinates of all the points in I have distinct, if they all had distinct xn values, then we would be in good shape. But here we change variables to xn goes to the summation of c sub I x to the x sub I equal and plus xn. I equals 1 to n minus 1, where the ci are in k are sort of random, or they don't have to be random, but they better not all be. If they're 0, you might never find anything. Okay. So anyway, so if you take random ones and you do this, once you change this variable, then you get, so for general C, so you don't know if you'll get it yet, but for general C, what you get is that the Grobner basis of I change variables to this of let's say obtaining an ideal I prime. Okay, so in other words, I've made the change of coordinates and I get I prime, and now I take the Grubner basis of I prime is going to be in the form x1 with lexicographic order. Remember we did x1 greater than ... greater than xn. Then x1 minus, it'll be g1 of x n ... xn minus 1 minus gn minus 1 of xn, and then it will be a g sub n of xn. And the degree of this will equal the degree of R mod I in the general case. So R mod I, we can, once we have in this situation, we can easily calculate this degree, and we make a change of coordinates until we get the dimension matches. In other words, until we get this as it matches. And once that's the case, then we can factor this. So the final step, so this is part D still, I guess, D continued, is that I prime is going to be equal to I, so Gn now we can factor it. And if we call that one P1 to the M1, PR to the MR, I hope that I'm using all of these in a sort of generic situation. Every single one, they're obviously going to be different and so on. So, but I don't want to get involved with all that notational nightmare. So this thing is going to be I prime plus the radical of this. That's what we're doing right at the moment, is that radical of this intersect ... of I prime. Actually, to tell you the truth, is this really what it's going to look like? A little sanity check on what this is. At this point, it can't actually equal this. I mean, this is too general for it. Why? Because at this point, every fi of xi is irreducible. Therefore, it's square free over a perfect field, and therefore it's radical. Therefore, the powers here have to be 1. So in fact, we get that this is actually equal to P1 to PR. Note it's square free. That is a consequence of the Seidenberg lemma. That's the only way, in fact, that we know that. And now we don't even need radicals here. But all of these ideals will be radical now. This thing is equal to this ideal plus this ideal, and each is radical. Okay. Actually, it's better than that. Each is radical and prime. So now we've finished the whole thing. So step 1 is we split it as far as we want, but at least to make it, we're doing the radical. We split it as far as we want. We don't have to go all the way. As long as it's radical, we can immediately go to the step D if we want to. But it turns out that in general, divide and conquer is a better notion, where if you make it into a lot of smaller things, it's better. It's not always the case, but it's a lot of times the case. And now we have this. Now, suppose now we have that I, the radical of I, is equal to, say, P1 intersect ... intersect some huge number of PNs, okay? We don't know how many. Maybe there's 1, maybe there's a lot more. And we've now somehow certified that each one of these is prime. By the way, what happens if we keep doing this 100 times and we never find the C's? What do we do then? We have 2 options. One of them is we can cry and go home. The other option is that we extend the field, so we have more random elements, okay? So if it's over the rationals and you're not finding anything, then you've got a bug somewhere, because there's no way that that's ever going to happen. But if you are, if you're over Z mod 2 or Z mod 3 or even Z mod 5, it's very likely that you will not find things. So you might have to extend the field to the finite field of order 4, 8, maybe 16, who knows? You can't change the characteristic if you really care about that characteristic. So but you can extend it. But then once you extend it, you get the answer over the extended thing. So what do you do then? Then you have to combine it down to get things that are over your other field, and that's a different issue. We're not going to worry about that. Okay, that can be done though. But this is the whole thing. Oh no, it's not the whole thing. This gives us all of the minimal primes and therefore the associated primes. So this gives now all min primes and associated primes, which are because they're the same thing. The same. Okay. That's one nice thing about the zero-dimensional case. And in fact, when I first learned it, I thought that the zero-dimensional case was so stupid because it didn't have any of the complexities. But it has a huge amount of complexity as far as actually doing it. But luckily, not all of the complexity. So it's a good loss of complexity, not sort of stupid one. Okay. Now, how do you get the Q's though? This gives us all the primes. How do you get the Q's? Once you know what the P's are. Oh, by the way, this is the radical of I prime. So in other words, you have to take the inverse change of basis and then take those ideals and put them back in the original set of variables. Okay. That seems like a fair amount of work, but it's something that you can easily write up in Macaulay 2 with some effort. But how do you get the Q's? Well, if I happen to know that one of these things is prime, at each step, I'm adding in something. I can keep track of this thing and the I plus pi to the mi power. And because I have that this is an intersection and that this thing, the radical of this is this, so if I eventually get it down to primes, I can do it. Now that might sound a little fishy, and you have to actually check that out that it works. But another way of doing it, so one way to get the p primary decomposition is to keep track of both the primes and the primaries as you go. Okay, so keep track of both the primes and primaries, primes and the prime and primary as you go. But another way of doing it would be the following. Another way. Okay, this is step E. Okay, that gives us this. This is step E, find the primary decomposition. Okay, so one way to do it is to keep track of it. Another way is we've got to the point where radical of I is equal to P1 intersect Pn. And now for each one of these things, we know right now that the radical of I will be of the form Q1 intersect ... intersect Qn. We just know that because we have all the primes. And because there are no embedded primes, these are unique. So how do we get these things? I think we did that last time also, somewhere along the line. We took splitting polynomials. So we let so for each, I don't remember if we did it for each I or each j. For each j, say, let's let fj equal the product of, no. We're going to choose an element in all of them except for the one that it's in. So choose this is in the intersection of the pi's, I not equal to j, but not in pj itself. The fact that there is such an element is essentially prime avoidance, and so you have to that takes a little lemma in commutative algebra to show that that exists. But then once you have that, you can then qi Qj, say, is equal to I colon Fj infinity. Okay, so if you don't mind doing it like a Grubner basis type calculation to compute this, you can get those directly. If you don't want to do that, you can do the bookkeeping involved with finding the primaries as you go. Okay, so that's the whole algorithm, really. Any questions about it? Was I vague or did I leave out some part? It's pretty easy to do the inverse. This is just a nice linear, where is it? That's a nice linear change of variables. Each of the other xi's just go to themselves. So I have an n by n matrix over the field, which is mostly the identity matrix and a bunch of c's. I just have to invert it. And that's like no work. And that's going to give you the inverse ring map. But I say that in a flip way because you have a 50-50, or actually 25% chance of getting it right, because you have to take the inverse and you have to put the x's on one of the sides, or you have to transpose it and put the x's on one of the sides. So you have to do a little bit of bookkeeping and figure out which way the inverse map goes. It's not very hard, but it does take a little bit of thing. So I thought we should try doing one of these things. Okay. Any questions about it before we do that? And also I cannot remember for the life of me what the Zoom link is. So what I think, maybe we should try to put this down and do it from here. I'm not sure how to do that. Okay, well, that's actually looks good. Okay, now. So I'm going to do this in Emacs, I think. Okay. Oh yeah, right. Okay. What time is it? Okay. Yeah, I think what we'll do is we'll play around with this for a bit, and then maybe I'll let you play around with it for some, and then we'll come back and talk about how to write all this into packages and stuff like that. After the and a break in there somewhere. Okay. Okay, thanks. I forgot that it was gonna. Okay, and actually we should probably, can we close
Lights.
yeah, some of the lights. I don't know if it does both. Which is
Ooh.
fine with me. Is that okay with everyone else? Okay. If you need to like take a little snoozy nap here. Okay. So I am going to grab, oops, the week 9 file, which is on the, okay, let me make it, oh, that's way too small. Okay, sorry. Can you see that at the moment? Okay, now I have a bunch of functions here that I just wrote to get us started on this, and so you can use it. Okay. Part of what you're going to do is figure out how to use those things and so on. Yeah, yeah. So under week 9.m2. And so here, and I just restored it. So I'm starting with, I think, exactly what's on the GitHub site. So I'm going to hit restart. Oops, that did not work too well. Actually, wait, where directory am I in? Okay, I'm in the right directory. So let me make this a little larger. Okay, so those look sort of visible to me. Are they okay? Okay, so I'm going to load this package. Sorry, it's not a package. It's just a bunch of, that's going to be one of the things we have to deal with. But right now, it's just a bunch of functions. I do want to sort of give you an idea of what these functions do. Okay, this one, I think we're just going to, I use this function all the time. So in fact, I'm going to dump this if true or whatever. I'm just going to do this, okay? When I like to see an ideal by having it inside of a netlist thing, because otherwise I can't tell what it is or anything. And So I'm going to just put that here. That's just a thing. Now there are three functions already in the system called denominator. If I give you a fraction in some fraction field, it will give you the denominator of it. A GCD of two elements will give you something, and factor will factor a polynomial. They're all three annoying in the sense of what we want to use them for here. So we are, well, right at the moment, it doesn't matter. We're not going to be using the denominator stuff. That's for when we go to the positive dimensional stuff. Right now, I think more what we're going to use is the following. We're going to use the univariate function. So this is how we want those f sub i's. That's actually really crucial. And we have a couple ways of doing it, but the simplest in Macaulay 2 is just to use the the already created eliminate function. So this takes an ideal I and it eliminates all the variables in this list of variables and keeps the rest. And the way it does that is it makes some sort of elimination order where it puts these variables first and then all the rest of the variables afterwards. Okay. And this line here, if you look at what, whoop, that was not so good. So what happens here is this list, this looks pretty complicated, but what we're trying to do is get down to a single variable v. Trouble is, in Macaulay 2, you don't give just the variable, you give the ones you want to eliminate. So here is all of the variables. You take the set of all the generators of the ring minus this is supposed to be one of the generators of the ring, and it just makes it into a set, and it just keeps all the ones that are outside of that thing. We make it a list because it's a set which is not useful, and then just to clean it up, I sort it into order. R sort is reverse sort, but that's actually what you want typically for variables. And then we eliminate, that gives us an ideal. And here I'm saying if number of generators is not 1, then my logic is wrong. I think we actually looked at this last time. I might have mentioned this. And then we factor it, but using the current factorization program, which gives us a list of pairs, and we just take the 0th guy, and hopefully that's the correct thing. Okay.
Like you've got this ideal J.
Yeah, so J is then we take J underscore 0 is J should be one generator since it's in one variable. There should be a single element in there. And so this is a polynomial in one variable, and then we can factor it. We could do factor of it, but then we have to unpack all the data from it. What do we want? The data are the p sub i's and the m sub i's, right? So this my factors takes care of that. Now it might not do a great job of, we might have to worry about some coefficient out front or something like that. So we'll have to make sure that that's correct. Univariates, by the way, is just taking it and doing it for all of them. Okay, so just so we can see how it goes, and it does univariate. It just does this. Actually, I might have put factor in at some point. It says list of factors. Oh no, each univariate is giving you a list of factors. So this is just calling it for every variable in the ring. Okay, so now I want to come in and we're going to do this on this first example. This is the one we talked about last time, which was that oscillator example. Yep.
So just going back to I just have
Sure.
so I see right above it, you just instantiate a method object, call it univariate, and then you give the rule which gives the method for univariate.
Yeah. So I actually, when we talk about packages, I will mention that this is the way I tend to always, you could just write a function, univariate equals v comma I gets something. The trouble with that is that when you look at it later, you have no idea what v and I could be. The only way you can tell is if you were happy enough to write down what it says and that it didn't change in the meantime after you commented it, which is, it happens a lot that it does change. But so this will at least give me, it will say I'm calling that on V has to be a ring element and I has to be an ideal. Now there's lots of checks here that should happen that are not happening right here. You should really check that V is a variable, not just a polynomial. You should check that the ring of these two things is the same thing. So this is not bomb-proof code. It's just for, hacking around like we're doing now, okay? But I didn't want to sort of, it can get a little overwhelming if you start putting lots of checks in. I did want this check in because I want to make sure that we're using it on zero-dimensional things, and that somehow it wasn't giving us more than one generator, which it should not do, okay? But this is the way you do a method. You have to set it like something like this, tell it it's a method, and then you can do a univariate of ring element comma ideal. You do a colon equals, and then this is a function, arguments v comma I, and goes to the body of it. Yep.
I think you just said something that's important for me. I don't actually know when I should be putting checks in if I'm trying to make bomb-proof code. Would we be able to talk about that later?
Yeah. So we might take this and try to make it more bomb-proof when we're doing the package thing. And the reason doing it when you're doing a package is good, because what we want to do is, so I've just written a bunch of code. There's no tests in here. There's not even an example in here. This is like really bad code, okay? So what a package should do is whenever you do these things, you don't know if you come back to it, whether it was correct, whether you left it in the middle of some non-working state or whatever. So it's actually very useful to have a bunch of tests, and that's what we'll do when we do the package. A lot of it is getting that kind of stuff set correctly. And it's actually writing a package is very good, because then it also, since you have to write examples, you'll make sure that you write the format of how you want to call it like it will be convenient for you, as opposed to this really inconvenient way, which is what will happen if you just start typing something and do it. Okay. Anyway, that's that. So here is the example we started with. Okay. K was the rationals. We can just do it over the rationals. This is a polynomial ring in 8 variables. Remember, those referred to the cosine of some angle theta I and the sine of some angle theta I. The x's were the cosines, the y's were the sines. But in reality, at this point, it's just some ideal. It doesn't really matter where it came from, although it is a pretty cool thing. So here is the ideal that was just given to us, and we may be, part of our package will be to write a function that takes a graph and just creates that. Okay, because that's something that everyone needs to do, and it's kind of nice to just do an example of it. By the way, I can do CI here, and then it shows me the list of what the generators look like. They're all nice quadratic polynomials, except this one is linear. They're not homogeneous the way I've done it. These have linear terms here and so on. Now I can look at the dimension and degree. So dimension of I is 0. That is the zero-dimensional thing we're talking about here. So this is going to be something like that. And it's going to, and the degree of I is going to be the dimension of that R mod I. Okay, so it's 36, dimension 36. So if I do binomial primes, what do I get? Okay, so it's relatively fast. I think we did this last time, but what I can do is I can take 08 is the list of them, and I can do slash dimension. That'll tell us they should all be dimension 0. You can't have a higher dimensional thing, because otherwise the thing wouldn't be 0-dimensional. And sure enough, you get a whole bunch. Actually, how many of these even are there? There's 19 different primes. Okay, we could even do net list of it to just see it. 019. Not 019. Sorry. This net list 019 was wrong. That was 08, right? Okay, let's take a look at it for a second. Okay, I don't know about you, but I see a lot of trivial ones. 4y's and x4 minus 1, x3 plus 1, x2 minus 1, x1 plus 1. In terms of cosines and sines, by the way, what is this? This is the cosine is 0 and the sine is 1. No, sorry, the sine is 0 and the cosine is 1. So that's the angle 0. And actually with a plus 1, it's the angle pi. So these are, one can imagine, kind of degenerate cases or things that one can handle. And there's a lot of these things, okay? And then there's some other ones that are not like that at all. Although this one does have y3 equaling 0 and x3 minus 1 equaling 0. So one of the angles is the 0 angle, but then there's all these other guys that here, y4 is √3/2. So there's a 60-degree or 30-degree thing floating around somewhere also. So, but at any rate, actually this one here has nice angles. This one down here, not so much. Okay, but we'll get to that. Okay, so we can look at the degree of each one. What was the name of that thing again? 08. There's the list of all these. If I do degree, each one of these things, look, all of these things were just 1 point each. But this one here was 2 points. You can actually see the 2 points. Y4 squared, there's a y4 squared, so you're going to have a plus or minus root something, and then all the others are linearly determined on that. So this is pretty clearly 2 points. Or 1 if it factored somehow or another. And then the next one is 6 points, and then this one is 12 points. But we don't know, actually we do know, this is the primary, we just did we do decompose or primary decomposition? I think we did. It doesn't really matter. I want to do I want to check whether it's equal to its radical. And the answer is yes. So this one doesn't have any, we don't have to worry about the primary part. We're just looking for the minimal primes of this thing. And we have all of these that we would like to find. Okay. The radical, by the way, means that, yeah, so the primaries are equal to the primes. So we don't need to do that. By the way, this idea, all of those ideals that were nice were contained, were actually primes of this one, where each of the xi squareds could be plus or minus 1, and the y's were 0. So I'm going to call that easy. And now I can clear those out of I by doing a colon. I might have to do a saturate usually, which essentially does colon with powers. But since I is radical, we don't have to do that. So I1 is I colon easy. And if I colon back, I colon I1, I actually get that ideal back again. That's 16 points here. And those are 16 of the ones that we saw. Okay, I think. So now where were we here? In fact, I can check to see whether the intersection of these two ideals is this. With colons and when they're all minimal primes, this will separate things. You should think about that. We know how to deal with intersections of ideals and colons. So this thing here, this should be true, and it is true. Okay, and now the dimension of I1 is 0, as it should be, and there are 20 points left. And dimension and degree of I2 was 0 and 16. So we had 36 points originally, and this clears out 16 of them, but it still leaves 20 points. So we're going to now take I1 and try to figure out how to do it. Okay. So exercise A1 is try the functions univariate and all this kind of stuff to see what happens. So let's do it ourselves. Okay. Let's do univariate. And what was it? We have to give it a variable. So the variables are, let's just do x sub 1, comma, I1. Okay. By the way, I will check in the modified version of this thing also. But hopefully, if you can be running this as you go, that's actually great. Is it working? Do you have the file handy? Okay. So if I do this univariate, what do I get? Well, that's a good question. I'm going to do a net list of this so I can see it better. So I can almost see it better. How do I move this back? Oh, I see. No? Well, I don't, I guess. Anyway, so I get 3. Here, I can do it like this. Okay, I have 3 factors. They're all power 1. Actually, we expect them, since we know it's radical, we expect them to be power 1. But this, if we do this for every variable and they're all 1, that proves that it's radical without going through the minimal primes, which is actually usually a lot more work. So here, x1 has these 3 factors. Notice that it factors as degree 6 times 3 times 6 plus 3 plus 1. So the polynomial is of degree 10. But we think that R mod I is degree 20. So this is not in like normal position as such, okay? But nonetheless, we have 3 things. So what we want to do is we want to now take this and just add each one of these polynomials in, see what we get. Okay, so here, that was univariate. We can do all of the univariates. That's probably worthwhile. Here is what we get. There are 8 variables. Okay, now as is obvious from this, all the coefficients are 1, the multiplicities. Okay, maybe not particularly obvious, especially since you can't see the hard ones at the end. But notice that the degrees of the power, these add degree 9, 10. This adds degree 10. This adds degree 6, 7. So there's obviously, when you project down to that one variable, you are getting some collapsing of those 20 points. Those 20 points are defined over the complexes, but whatever. But some of them, this one is 12 plus 6 plus 2. That's actually 20. So in reality, right at this point, we could take this one here, and we know we're in the normal position for that, and we could factor this polynomial into these 3 things. So we already know that the 3 prime ideals are going to be the ideal plus this one, the ideal plus this one, and the ideal plus whatever this one is, because these are all irreducible. And then that's the answer. So what's true is that there is a full algorithm that you could do, but if you need to do it by hand, you can, and you can just you get lucky at like this a lot, but the algorithm might not, depending on how it's coded, might not see that luck, and it might go through a harder way of doing it. Okay, so let's go back to here. So here, oh yeah, so here I didn't take the easy one. Okay, that one we could just do and get the answer, but I don't want to quite do that. So what I want to do is I'm going to take univariate here. It's hard to see this, so let's do it this way. For factoring univariate of x1, so we're going to do the x1 one. And here, let's do it up on top and bottom. So here are the 3 polynomials I get, or the 3 factors. I get 2x1 plus 1, and then this one, which is 8x1 cubed plus so on and so forth, a power 1, and this is a power 6. Okay. Now, since we have 20, and these are the irreducible things, that tells us already a lot of possible things if we really needed to get into it, but let you think about that. What I want to do now is do the splitting. How do we do the splitting? I'm taking every factor in here, which is actually a pair of things. It's a polynomial and an index. And I'm going to take the ideal, I1. Remember, I1 is the simpler one that we're using. And then plus this ideal of fact underscore 0 will be the actual polynomial. So I'm adding I1 with that, and I'm trimming that ideal. So here's my J1s. I'm going to do this line, and I get 3. If I intersect those J1s, that's 3 ideals. I hope it's 3 ideals. Let's take a look. It's actually 3 messy, very messy ideals. Here's one ideal. Here's another one, and here's a third one. Oh, wait a second. Shoot. 1, 2, 3. And that one kind of goes on for a while, okay? So it looks bad. If I intersect them, they're the same. And the degrees of each one of these things are 2, 6, and 12, which add to 20. So in fact, since these are all, well, we don't know that these are all irreducible yet. In fact, we really don't know that. So what I want to do is look in the Lex order and see if they come out in that nice shape formula that we had. So I'm making a new ring here. It's the same ring as R, but I'm changing the monomial order to Lex, and I'm going to call that R Lex. Okay. Now what I want to do is I want to substitute all of those ideals into this new ring. Okay, and now what I want to do is I'm going to take the ideal of the Grödinger basis and do C of it, so I can actually see what each one is. So let's see the first one. Okay, What, did you get it or?
No, I've just been getting errors all over the place.
Did you load the notebook?
I tried loading it and then it didn't work. I tried that twice. It still didn't work. And so I had to go back and copy everything, load that in manually, and then now it's not working for a different reason.
Do you want,
I can just follow on this.
Okay.
It's okay.
but still, it should be, if you restart and then reload, then you won't have problems.
I did that twice.
Is it finding the file week9.m2 to load?
I think so.
Okay,
I can figure this out later.
okay.
So that file is
It has a what?
Well, there was a reload, the file says reload itself.
Actually, it doesn't.
Confusing.
So here is what it is. So this end, remember, this is a thing that if you see this end, and I put a minus on it, so it's easy to detect. Everything after it stops Macaulay 2 stops reading at that point. So you can put a little test stuff for yourself or how you're going to use it afterwards. And so I tend to do it that way. So this way I can put a few functions in here, and then I can do a load, restart and load, and then I tend to do when I'm working, I tend to like to start from clean, but not everyone does. Some people like to just load little bits. But then I find that you can really get into a position where it might work or might not work, and then it's hard to tell if it was a bug in it or you just loaded in not everything you needed to or something. Okay, so where were we here? We were right here. For x and univariate, we had done this, okay? And this one here, notice that this is in shape position. All these things are linear, and there should be 7 of them, 3, 4, 5, 6, 7, and then 1, which is actually an irreducible polynomial over the rationals. If you wanted this over an extension field, well, then you'd have to add that in somehow, and we could talk about that, but not right at the moment. Okay, now that's one of them. Oops, why did I do? Okay, now what I want to do is I want to actually see the second one too. I don't know where I must have run this one again somehow or another. But anyway, I'm going to do the L's I had written already, and now I'm going to do the Grosvenor basis of the next one. Does this work? Actually, it looks pretty good so far. X1 and then a polynomial of degree 4, x2, x3, x4, y1, y2, y3. This is also in shape form. We don't even have to do any checks of degree or anything like that. As soon as it is in this form, it is in shape form, especially since we know that this is irreducible. So this is a prime ideal here and it's over the rationals, you would have to take the roots of this. Notice that you can see that we would have to take we have a cubic polynomial, and then we have to take the square roots of that element. So there's a degree 6 extension of Q where all the solutions would lie. How about the last one? Are we going to be lucky or unlucky? Oh, that's pretty bad. However, it's linear in x1, and then it's a polynomial y4. Remember Lex, as soon as we see only a y4 in here, or any, then everything else after it has to be a y4 or a constant term. There probably is a constant term. x2, these are all linear. And then we get a degree 12 polynomial y4. So this one, and again, it's 2, 4, 6, 8, 12. So it's a degree 6 extension, which is sort of different. If you wanted to do some Galois theory on this stuff, you'd have to deal with what kind of extensions you have here and so on. But we don't really care that much. We know that this is a prime ideal now. Okay, so we've written that this I1 is an intersection of 3 prime ideals. Even though it didn't have the right degree at the beginning, when we applied it to this, it did. How could that possibly be true? It's an interesting question. How could it possibly be true? Well, what it means is that there's probably the value y1 that we used to split that thing, I think, or x1, whatever we used to split it with, did have some some. Actually, that's a good question. How could that possibly? I mean, what happened is that there's some duplication of the values of x1. They're probably each one appears twice is the likely explanation. Whereas when you plug this in, you're getting all the values of y4 in this, because we did the Lex order. Actually, that's a good point. We didn't really check that this is irreducible, have we? Now that I think about it, we just did it for the whichever variable we did, x1. This might not be irreducible. However, whether it's irreducible or not, this will be in shape form. So all we have to do is factor that and then add the equation. So why don't we try that? So if I take this ideal here and I take the 0th generator, I get this. Drum roll, please. And sure enough, it's irreducible over Q. So it's not trivial either. I mean, we started with a combinatorial object, this graph, which I don't know what the graph is here, but it was a nice graph on, I think, 5 vertices. And it's a really simple one. And yet, we're getting some bizarro field extension for the solutions. I have no idea. And I find it a very interesting problem. So as I said last time, if anyone's interested in talking about this or even investigating this, there is a package to generate all these ideals, although we'll play around with that first. Okay, so I guess actually I was going to have it, but we just proved that this thing is, we actually found the primary decomposition of this one. There's 3 things after we got rid of those 16 trivial ones. If we didn't get rid of the 16 trivial ones, we had a lot more work floating around. But we could do it. And actually, it's probably worthwhile exercise to try doing that and see how it goes. The trouble is that you're going to get lots of factors and so on and so forth. So, but still, it should be the case that if you take that first polynomial, you do it for x1 first. You factor it. And then you split it amongst that. And you get a bunch of non-zero ideals. Now, for each one of those, you take the second variable, x2 say, and you split each one with that. And then you take all the non-zero ones and you keep that list of them. And you just keep doing that for each variable. You should be getting the 16 plus these 3 in the end, because we did not need, all of these ideals are in shape form, as it were. Any questions about this? So maybe what we should do is, I think it's actually valuable to play with these yourself. So what I might want to do is I can give you another ideal that's that is 0-dimensional and try this stuff on it. I think I have one handy. There's one, I think cyclic 5 roots is like this. And I will write down the equations and I don't know. They're actually in the Jupyter notebook somewhere, but I can't remember which one now or where. So I'll just grab it. And I can explain to you what that ideal is. Maybe I should explain now, and then we take a break, and then you can play with that. So does this make sense? If you don't have Macaulay 2 handy, you probably want to use some of those functions at the beginning for that. And what maybe what I'll do is I will change the week 9. This is week 9.m2. It's really week 10. So, but nonetheless, I'm just going to add in one more ideal in there that is this cyclic roots and make sure that it's the right kind, and then you can play around with that one. That one I think might be a little, I don't know actually. A lot of times it works that you can do it directly without any change of coordinates whatsoever. In fact, it's extremely rare you have to work hard to get to situations where anything in practice, it usually tends to be quick, but you do need that kind of thing. Okay, sounds good. Let's take a 10-minute break and oops, can you all see that, or should I make it smaller?
Yes.
Okay.
Keep going, I can still see it.
Okay, I just added the following thing to week 9. So if you check it out from the GitHub repository,
Oh, okay.
it's after this example, we actually pretty much did that example, but here's another example in 5 variables, which is a little less. And it's called the cyclic roots. I actually sort of dislike these examples because they're oftentimes used as benchmark problems in computer algebra systems. And they are nothing like the usual things that that happen on other examples. They just have very different behavior. So I kind of think that they shouldn't be used for that kind of thing. But they nonetheless, this one happens. If I look at this, what is this? This is dimension of I, comma degree of I. Okay. Ooh, 70. That's a little more. So your plan is to you can try the Macaulay 2 routines. It's kind of good to do that, and see if you can see if you guys can split it up. Maybe use the univariate stuff that we did, the factors, whatever. See if it works. Yep.
I am new. How do I get this thing? You said it's on your GitHub.
Yes. So did you get the week 9.m2 file before, or
I
did?
did. That was on slides from the U of T thing.
Oh, I see. That was on slides. Yeah, actually, I think that he's on the GitHub. So if you go in, look for a repository of mine called coag, capital C, lowercase o, capital CAAG, right? You're in it. Good. Now look for, now inside of problems,
Week 9.
week 9. Yep, you got it.
Cool.
Now you can just download that file, I
Do I
think.
download it or copy paste?
Either way.
Okay.
So now if anyone doesn't have a Macaulay 2 handy, you should be doing this with someone who does. And doing it in groups of a couple is definitely a good idea because it's a very good way to, and much more fun than oftentimes just doing it on your own, but that's all up to you. My way of doing things doesn't necessarily match yours, so you can do whatever you want. A2. There's exercise, oh shoot. I didn't see exercise A2 and then I put problem A1 in after it.
That's a dash one.
A-1. Yeah. Okay.
Or A minus one.
Yeah, A-1. Yeah, I mean, it's a pretty simple example. Here, you can't really see it. All the example is this, but it's better not to have to type it in. So grabbing it from the GitHub is good. And all this other stuff are just a handful of things that some of it I just typed right now, but you can try all these things. Decompose is a synonym essentially for for minimal primes. So I used to always use that, but somehow I started using minimal primes. I don't know why.
Is your Macaulay 2 working now? I don't know. So if I click load, right? So it doesn't file. So obviously I haven't given it the path. So how do I find out where the path is?
Do inside of Macaulay 2, do run double quote PWD and double quote.
PWD.
Yeah,
Got it.
print working directory.
And
Yeah.
then I add all of that string in front of the document.
No, actually, that's you want to know where your week 9 file is. So when you do load of it, you want to put the whole path for week 9 in.
Put week 9 into where that is though, then that should fix this.
That should fix it.
Great.
Yes. Where is it actually?
It's in downloads right now, but the
Okay.
previous file that I was having troubles with, that I was trying to load, that is in where this is. where it's run.
So you might want to rename that one and then change it unless you don't
Okay.
care.
I'll give it a shot.
You want the whole week9.m2 file though, because so you can have all those functions that we were looking at.
Yeah.
And I'm happy to help out. By the way, if you want, you can do it over a finite field too. So it doesn't have to be done over Q. It's just in this, so oftentimes doing things over Q is much more complicated than over a finite field. Because the integers can get very large and so on. But in this particular case, I think that doesn't happen. Yes.
Sorry, I feel a little bit silly here. I don't actually know what the purpose of a problem A-1 is.
The purpose of it is to not use the built-in minimal primes command, but to try to find all the minimal primes using the stuff the algorithm we've done today. So that means like, take the ideal. Okay, you can see the dimension of it, the degree of it. You can use some Macaulay 2 stuff, but the idea is that in real life, oftentimes if you type minimal primes, it might go into Never Never Land, and then you want to know somehow what you could do in that kind of situation. In this particular case, it comes back much faster than you'll ever be able to do it probably, but it's a good example to sort of make sure that you know the algorithm basically.
Okay, sweet, thank you.
2 more minutes, okay. Oh, how far did anyone make it?
A couple steps, not very far.
Yeah, okay.
It seems to keep just wanting to keep on going.
Okay, well, actually, that's an interesting point. I haven't actually tried this one, so I'm hoping that it will work out. But okay, so let's go back to whoops. Am I sharing? Yes. Okay. So let's find our example. So I'm going to restart and load this. Well, I guess I don't. I'll just redo this. Okay. So there are a whole lot of minimal primes. Dimension is 0. We can do the primary decomposition. Ooh. Okay. And it is radical. Okay. So anyway, that's just getting used. That's the kind of thing that you will almost 100% of the time do. But if you ever in your work come across an ideal that it doesn't work, then you might play around with all these methods, right? Okay, so I'm going to do this univariate A. Is this large enough? No, maybe one more size up. Okay, so we have 5 variables. I'm going to take this univariate A and just see what it looks like, okay? So I have this. I can't really see it because of the size. So I'm going to do net list of facts. Okay. So this polynomial, the I intersect the ring with one variable a in it, has an element which is the product of all these guys, right? And so we have 5 different things, and they're all power 1. So far, we don't have any evidence that it's not radical. Okay, but that doesn't mean it's radical. So what I'm going to do here, oops, that doesn't, here, let me do it this way. Okay, so I'm going to now take the list. What I'm doing is I'm trimming it. I don't really need to take the Grosvenor basis of it. I could just trim the ideal of it. And actually, I don't need to. I'm not sure which is best, to tell you the truth. Trim cleans it up a little bit and get, but I don't know if that's helpful here. Sometimes it's not. So I'm going to call this J's, I's. How about I1? Okay, I was one ideal. I1 is going to be a list of ideals. Maybe I should call it L1. Oops, it didn't work.
Missing semicolon.
What the function is that?
Wait. Something's wrong. If I do that. Oh, I see. It didn't like that way of splitting things up. That's interesting. Let's see if I can do it this way. I'm trying to get it so it doesn't look so awful. No, it's wanting to do that. So I can put an open parentheses here. Let's try that. Okay, now here's L1. Let's take a look at L1 should be 5 ideals. Okay, so if I do L1/dim, that I get 5 zeros, as it should be, unless I made a mistake. How about the degree of each of these things? Those should add up to 70 that we had. It just can't be anything else. Once we have 70, it will, unless we actually find a non-radical thing where the number will go down. This should add up to that. So now we have 5 ideals. The 4 is probably pretty easy, but what I was thinking of doing now, and what you maybe what you did was you actually took one of these and then tried to find its univariate polynomials. Another option we could do is for every single one of these ideals, L1 has 5 ideals, we could take every factor of fac and add it in. But maybe what we do is first, let's just do the first one and try it out, okay? So I'm going to take L1_0. This is my ideal. It looks like kind of a mess still. So what I'm going to do is I'm going to do in univariate of B comma this, okay? And I'm going to call this facts again, even though it's different from the previous one. Is that okay? And oops, I don't want to net list it. So this time I have 3 factors, not 5 factors. By the way, if you did it at the beginning, you will have found 5 factors for all of them. So what this means is that it already cleared out 2 of the factors as not being necessary. B-1, that's a pretty good one. Actually, these are all pretty nice. This is like a 5th root of unity, so on and so forth. So what I'm going to do now is I'm going to do the same thing as this. Okay, maybe we should make a function out of that. So I'm going to take, for every fac and factors, I'm going to take, but now it's not I, it's going to be L1_0, and this is going to be called L2. Okay, does this make sense? Are people paying attention to what I'm doing? Okay, so if I'm not saying anything useful, let me know. Okay, so here L1_0 is the ideal. We're adding to the factor, and then we're taking all those ideals. So let's see what we get here. Okay, and if I do net list of this, look at this, it's split it up. I mean, actually really quite nicely. but I don't know if those are all good yet. Note, look at this one. This one has one variable and the others all appear linearly. So this one is going to be in normal position, at least if I had chosen C to be the last variable. Okay, this one is a little harder to tell. Here I have a DE and a D squared. So I suggest what we do is we try for these, we try making a Lex order and just see if these are in normal form and if they're prime. Or we could try splitting them with respect to the next variable. So actually, so here is one way we could do this. So here's how we split we've split one ideal by all of those things, right? So maybe we should make a function that that takes a variable and a ideal and splits it into a list of things. Okay, so I'm going to do that. So let's call split ideal. Okay, and I'm going to give this I'm going to make it a method just because I get confused if I don't. Split ideal. It's going to take two things. It's going to take a ring element and it's going to take one ideal. Okay. Maybe we call this just split. Okay. So this will split the ideal. So, and here, this is going to be a var V and an ideal I. Okay. And what this is, oops, I screwed up. This is not an arrow here. That's a colon equals. And it's returning, the way you give it the return value, this is going to return a list, and I do that. You don't need to do that if you don't want, okay? But you have here's how what are the types of things you're going to allow to do it. Then you have a colon equals, you have the return type. It's just a suggestion, you can always change it and really screw people up. And then this here is actually part of the return type, really. And then you have the arguments, which should be one of these and one of these, and then you have the body of the function.
Wait, what do you mean by a return type?
So the function is going to return something.
Yes.
What is it returning? Is it returning an ideal, a list, a matrix, and this, if you tell it this, it doesn't actually use it, to tell you the truth. But what it does is that when you read it, you say, oh yeah, this is returning a list. So you don't have to go into the code and figure out what it's returning.
So when I've made a method in the past, the way you return something is just leave it unsemicoloned at the end of it.
Yeah, that's right.
And so what this is saying is, aha, whatever is unsemicoloned in my method, actually that's now a list.
No, it's saying I am telling you that whatever I return, either by a return statement or the last thing, which is what you're talking about, that thing had better be a list. Okay, I'm saying it's list. It isn't always a list. Sometimes you might have a thing where you say you might want to return null if it doesn't work for some reason, and then return a list otherwise. So it's really it's more of a documentation thing. Yeah, it's not enforced at all. And if you're going to return lots of different things, then you don't want to have that. But usually you will return one thing. Yep.
When you have a method that you have different options, and depending on the option, you have a different output, what you should do that too.
Yeah, I think for me, so the question is if you have you have optional arguments, and each optional argument, you want to return something different. I think that is probably, you might want to just design it a little differently, because that can be very confusing to use. You could do it, then you just don't give a return type here and do it.
Polymorphic, where.
Yeah.
Is it just by the number of arguments? Or type of
It's by the type. So it's dispatching, not just in Python, it would dispatch on one argument. You have the type dot something, and it will dispatch on what that is, and it will look for a member of that type. Whereas here, it goes through and looks for, if you give it two things, if the first is a ring element and the second is an ideal, then it will call this one. But you might have other ones. In fact, that's why I changed it from split ideal, because I'm going to call this on a ring element and then give a list of ideals later, and then we're going to split a whole bunch of ideals at one shot. So I thought we'd just try this out.
So does it try to find the most specific match?
Yeah, it has an algorithm for doing that. There's a you know, sometimes if it can, if one of them is exact, if it's, both of them are exact, it's great. If not, you know, there's an algorithm for doing it, and it can get confusing if you're not, if you try to do lots of that. But I have to say, this multi dispatching on more than one thing is really useful for the math stuff. Yeah.
Sorry, just to return back. So if, let's say you say that the return value is a list.
Yeah.
Return type is a list, and then what you've actually spat out at the end of your method is not a list. What does this do now?
So it will do nothing.
It just won't spit anything out, or?
No, it will spit out whatever you tell it to spit out.
So you could be lying to your reader.
Absolutely.
Oh, okay.
Okay, so, but in the documentation, it will use this in the documentation.
Okay,
And it will complain if you say it's something else.
okay.
But it's documentation. The first two are not documentation. That is used in dispatch. This one is just more, that was a kind of recent thing. And we used to have typical return type or something like that. But in fact, it's much better if you know what it is to say it, even if it isn't checking it. It would, maybe in the future we will check it, but it's not checked now. Okay, so let's try this, okay? So what are the steps? I'm just going to do all the ones we had. Facts is going to be univariate of the variable v comma I, okay? And now what I want to do is for every, I'm going to just, this is going to be split with radical. I'm going to totally ignore the higher variables just for the moment. We could put that in somehow. We could actually say it's higher than 1 if we want, but maybe this should be called split radical. Okay. So I'm going to call it split radical, just so we know that we're only looking at the one things. So that's one. And then what I want to do is for fac in facts, I want to list, and then I'm going to list this thing here. Sort of, but we have to make sure we have it right. The L1 underscore 0 is actually called I here. What did I just do? It's called I. Okay. So I'm taking a Grosvenor basis, trim ideal of it. I'm doing this in the original ring, which is usually not a Lex order thing. And you'll find that if you try to do saturations or ideal quotients or, you know, any of this kind of thing in a Lex order thing that's not zero dimensional, at least, is going to take a lot longer and be a lot more complicated output. So you'll find that sometimes Lex is good, but most of the time Lex is bad. Okay. So anyway, this is now returning. So wait, where is this? That is returning the whole thing. Okay. So this is returning this. So what I usually do is I sometimes put a little thing in here where I can test it. So I'm gonna just F11 this through, although we should really put it up above in the thing. When we do a package, I'll show you how to do that. And we're going to do that in just a bit. Now I'm going to call split radical on I. Okay. And I'm going to call this L1. Oh, sorry. Triple slash is an alternate way of doing list of strings. So it's just making a string in the middle. So it's not, it's just going to return a string. It won't do anything. But this allows you to have double quotes in it without escaping or anything. Yeah, it's probably like that. Okay, let's see. Here is, oh, it didn't like it. Why not? Oh, I see. I have to give it a variable. That makes, so I was using it incorrectly. So I do this and I get these ideals. So I'm going to do net list of L1. And I get my 5 ideals. Just like, this is exactly what we had done before. Now I'm going to add a new method. Okay, split radical, but now it's going to take a list of ideals. Okay. So V and then L is going to be the list of ideals. What I want to do now is I'm going to call split radical for each one of those ideals. Okay. So for I in the list L, I'm going to list split radical of I of V comma I. Does this make sense? What we're doing here? So this is split radical. I want to apply it to every element of this list of, I have a bunch of ideals and I just want to split each one without doing it one by one. So I just want to go through the whole list and do it. So this will split each one. But it will make the result will be a list for each one of these things. Okay, so the result of this is a list. And the result for every single one of these is a list. So this is going to be a list of lists. So I can make it one list by just doing flatten of this. Okay. So this is my new function. Do you want to see that again? Okay. Now what I want to do is I'm going to call split radical of L1. Oops, I've already done it with A. So now I'm going to do B with L1. I'm going to call that L2. Okay. And let's see how this works. Okay. By the way, if I do intersect of that, of L2, what should I get? Actually, if I do intersect of L1, what should I get? Yeah, I, right? And it's true. And here I should get the ideal I started with, which is I. It's I've split all of the ones that intersected to I, and so the whole intersection should be I as well. Okay,
Oh,
so
I got false. Neat. Okay, anyway, sorry. Go ahead.
yeah, right. You might have yeah, I don't know.
I'm honestly getting both, so I'm restarting it. Let's see. What's that?
Yeah, if you yeah, at any rate, now I'm going to do L3. How many do we have, by the way? We've just split it into 13 ideals so far. Okay, so if I do net list of L2, I have all of these ideals. A lot of them look really nice and simple, but they're not completely simple. And the reason they're not looking completely simple is they're not in Lex order. Probably if we just do Lex order of all these, it would work. But in fact, instead of that, I'm just going to keep going. I'm going to do L3 equals split radical of C comma L1. Okay, L2. Okay, so I've calculated L1 first, then I made a whole lot of ideals L2, and now for every single one of those, I'm going to split with respect to the next variable. It's done. How many do we have here? 17. We went from 13 to 17. So it's still splitting it somehow. Not all of them split though, but a lot of those stayed the same. Okay, and now if I do net list of L3, what do we have? We have a whole bunch of relatively straightforward ideals. There might be some slightly nastier ones in here somewhere. This one almost looks like it, oh no, but there's more after that. It looks like it could factor, but it doesn't. I mean, but anyway, I'm going to continue on, okay? I'm going to do L4 equals split radical of L3, okay? And now how many of them are there this time? What did I just do? Okay, I do number of L4, it stayed the same. Oh, that's because I split with the same thing. So that wouldn't ever help because they're already irreducible with that. So I'm going to do D. And how many do I have now? I have 20. That might even be the actual number in the end. But we have one more to do. L5. And I'm going to split L4 with the variable E. Okay? And now how many do I have? Number of L5 is 20. Okay, now I'm going to do a net list of L5. And I have all these ideals. Okay, so now we have to figure out if these are in normal form. So these are all ideals such that if I look at their univariate polynomials, they're all in it has 5 univariate polynomials, but it will have other stuff in the ideal too, because we did I plus all those things. And so now we have to let's see how it works. Okay, so what I'm going to do is I'm going to I wanted to make I'm gonna do RLX is equal to QQ, actually just new ring of R, comma, monomial order gets Lex, okay? And now I'm gonna do L5, maybe I should call it L5 Lex. And what I'm gonna do is for each ideal I in L5 Lex, or in L5, little I is an ideal. I'm going to list and I'm going to substitute that ideal into L5 Lex. Okay. And I meant R. Oops. Yeah, that's exactly what I meant. RLX. I'm substituting the ideal and I'm going to take its Grosvenor basis of that and we make it into an ideal just so I can see it easier. Okay. So does this make sense what I've just done? So so I have I've done all the splitting possible. Anytime I have a zero dimensional one, I could just do exactly these lines for one per variable. And then I have, let's see, I don't know if we've done L5 Lex. Yep, we had, but we do it again. And now I'm doing L5 Lex. I'm going to do for every one of those. I'm going to do that. And let's take a look at that. I'm going to do net list of each one of these things. Let's see how it looks. Okay, we should probably write a function called in normal form, but here I see e squared and then I see all linears. Here, this is very interesting. Is this in normal form? It is not for that specific set of variables, but if I were to put d in the last variable, it would be in normal form. And same with c here. So that's actually an interesting thing that happens here. How about this one? Is this in normal form? A is the lead term, B is the lead term, C, D, and E. Here we have E squared, A, B, C, D. Here we have, again, it's going to be in normal form if we switch the order. This one looks like a bit more of a mess, but if you think about it, there's a D, there's a C, there's a B, and there's an A. So this one is in normal form. I think they're all in normal form, actually. Obviously, we want to write a function because looking through all these is completely error prone.
So don't we need them all to be in normal form with respect to the same Lex order?
No.
Okay.
What we can do is we have our ideal as an intersection of ones. So we're really handling each one separately. So that's part of the problem. If we tried to do it in normal form before splitting, we're out of luck because it's not in normal form for that kind of thing. But once we split it, it can be normal form for different things. And in this case, I think this is actually, we can actually, what we can do is that we can do L5 slash is prime and see if they're all prime. And are they? Tally 00, and they're all true. So they're all prime ideals. And if you needed to you wanted to figure out what the actual solutions were, you have several options. One of them is you could do you could just find the roots numerically and you do that, or you could see what extension you need. If I add a primitive fifth root of unity, I get those. Same here, here. Ooh, I don't know what this one is. Okay, so anyway, so that's sort of one thing. Yes. So this is the code that so I will put this in. So we added these split radical functions. Okay. We can add another one now where we just loop through all the ring elements in the ring, and then that would give it to us all in one step. I mean, it would be doing all of this work, but we would not have to be hand-holding it. So this one is factoring the univariate polynomial with whatever variable we give it. For every one of those factors, it's computing I plus that factor. It's totally ignoring the multiplicities. And but it gives you all those ideals. Here, for every one in your list, it gives you a list. So this is a list of lists. So flatten makes it one big flip and list. And then we did that each time, and then we would get that. So in fact, if we wanted to, let's try one more thing. Let's do split radical. And now I'm going to give it a list and a list. Okay? And the first, and it's going to return a list, and it's going to be var list is going to be the first variable. And the second one is going to be L, which is an ideal list. Okay? And now what we're going to do is for V in var list, actually, let's do answer will be L. No, we want a split ideal. We want this to be a single ideal. Yeah, we want this to take an ideal and split with respect to all these variables. Okay. So this is going to be an ideal I. And then we're going to let L here be equal to, I guess, to I.
So when you declare a list, can you specify the type of
No,
list?
no, it's totally not doable at the moment. We would like to do that, but that's not part of the language. So for V in var list, I'm going to list split radical of the variable comma my list L. Okay, and then I'm going to flatten this, and actually I don't want to flatten it. Actually, this is not quite what I want. Here, what I'm going to do is I'm going to do L is equal to split radical of L. I don't need the list. I just want the final value. So L is going to be the thing. So I'm going to do for each time I'm going to split the radical of the list of things I start with. And the first I'm starting with just one. And then I'm getting more and more and more. This is doing all these things one by one. For each V in the variable list, we get that. And to tell you the truth, we could probably, we can even do better. But let's try this and see if it works. The chance of it working is small. But what I'm going to do is split radical of the variables A, B, C, D, E. Actually, let me use the ring R to make sure we're not in the other. Oops, I screwed up. And we're going to use the ideal I again. Okay. And it didn't return anything because I forgot to return anything. So I have to do it like this. So L is my answer, and I keep writing over it, and then I'm going to return it. So let's see if this works. I have to reload that. Now I come down here, and I do split radical, and here it is. Number of O102 is 20, and O102 slash is prime is true, and tally those, we get 20 truths. So we found the 20 minimal primes that way. So this would be one way to, I mean, this doesn't actually do it. If they're not prime, you have to do more work. But at least it sort of handles the almost all the cases, except for the hard ones. You got it?
I think so.
Awesome. So I will put this this new week 9 thing. I will check it in also. It's week 9 dash answer. But I think should we do some packages now? Or I can save it for next week. No, I think I should do it this week because for your projects, it'll be handy thing to
Take
do.
a 5-minute break.
We can absolutely take a 5-minute break.
I'm not getting the right number of things in my list.
What are you getting?
I'm only getting 5 things.
Ah, then you're not doing a flatten.
Did I forget to flatten? No, you didn't flatten.
Oh, I didn't flatten it. Oh, no, that's right. That's because I did the flatten in this one here. So this flattens it. And so this L has already got the flatten out there. So do you have that flatten in?
I do. It looks like it's only doing one step of the recursion.
So maybe what you're doing is, what did you set L to be the list I?
Yeah.
And you gave it the ideal I you started with?
Yeah. Oh, you're. Oh, okay, I see. when you define L inside the for loop, you're feeding in L. I was feeding
Yes.
the ideal. That's what.
Yeah, that's true. That would, there.
That took longer, so that's a good sign. There we go. Okay, cool.
What does it do the doctor?
What does this function do? Okay, so do you understand what the other ones do? Okay, so this one, it first, it makes a list of just the ideal I. And that's because we're going to be calling this function all over and over, and we don't want to have a special case, whether we call this or this. Okay, so what this does then is for every variable in the variable list, which in our case is A, B, C, D, E, what it does is it calls split radical on that new variable on whatever I had before. So initially it's on the ideal I. And so it returns a list of ideals. And I'm resetting L to be that. Then for the second variable, I'm splitting radical of that new variable with that older list. Yeah, so this is doing exactly these things. L1 is split radical of this, L2 is split radical of this, but it's as if I called this L, this L, and this L, and this L, and so on.
So I keep it. And when it stops.
Oh, this is for it stops for every, it does it for every V in the list var list. So if you give it variables A, B, C, D, E, that's what it would do. Sorry, what? Absolutely. So this might be doing more work than it needs to do. But on the other hand, typically, at this point, the ideals are all pretty simple. They don't have to be, though. I mean, on hard cases, you might find that this is a really inefficient way of doing it. But you might also find that it works better than even the implemented version. So, different ideals have different behavior. So, it's a question of how did it choose correctly which algorithm should apply. I've only really shown you the one algorithm, but it's, I think, the best and most flexible of them. Here, let me get the project. Package stuff. So I'm going to call it, well, I'll wait and do it while we get started here. Are we all here? Should we start yet? Has it been 5 minutes? No, a couple more minutes. Let's wait. So we'll do enough about packages to get you started, and then next time we can do a little bit more as well. Who's done packages before? Yeah. That's right. You've just done that. Really nice one. That's good. That was great.
What was the package?
And now it's
Yeah. By the way, if you wanted to do a little project where you would describe your package, that would be a possibility. That would be kind of cool. That would be on April 21st, I think, is that date, is when we will do those.
Yeah, I mean, yeah.
Okay.
What was the package on?
It's the homology of line bundles and the instance correspondence, the main thing. Like we cover the dimension and the characters of the homology, but we also stuff to after the multiplication Adamski representation and some function to check if something has the reflection property.
I see. So you might have to explain some of those words to us.
That was one of the easier.
Yeah, no, but anyway, I think that would be great. Okay, I think we might as well do some packages now, okay? Okay.
Oh, just
You want to see this?
I actually tried it. And it's just the
And a what like an exercise would be, what do you do? I mean, how do you actually? I mean, we still haven't written the code that checks whether something is normal form, therefore prime, or what to do if it's not. or what to do if we're totally ignoring multiplicity here. We are getting all the minimal primes, that we're not losing anything. But we are losing the multiplicity information, the primaries. So anyway, so this is just part of it. Okay, so I am going to start with, we're going to call this my package dot M2, okay? So I have it, can you actually see? Unfortunately, it's very small. So we're going to put something in here. And maybe a good example, we could actually put these three functions in. And we'd have to put the univariate ones in too. So actually, I think slightly easier for the first time is to make these ideals that we did for the oscillator ideal. Okay. So how do we, okay, I've got a blank file here with my package. Now what? So here's the thing. If I'm running Macaulay 2, I can do the following. So I'm going to put this in here. I'm going to put a comment in here. Use print package template. And then I'm going to give it my name, which is going to be my package here. Okay. So I'm going to use, I'm going to put a colon here because that's not part of it. So I'm going to grab this line here. I'm going to come over here and I'm going to do this print package template of my package. And it just did a whole bunch of stuff. Now I'm going to copy and paste it. I mean, you could do it and put it into a file yourself. You know, you could, but right now this is the whole thing. So this is the whole package template here, and I'm just going to save the file. Now I'm going to make it larger so you can see it. Okay. This is the template for a package. When I make a new package, I start from this template and start it. Okay. But there's a few things that one has to do first. See this headline right here? We have to say what it does. This is my very cool package, which does, frankly, nothing. Okay. So it can't be too long of a line either. It will complain if it, I think this is okay, but we'll find out.
You define too long?
Yeah.
Larger than 100 characters. I forget what the number is, but the idea is that this is going to be used in a list of other packages. So if it gets too long, it'll just look awful and stuff like that. And also, you want it to be something quick that says something nice about it. Like you might say, you know, computing coincidence, homology of line bundles, or or something like that. Okay. Now there's going to be all these things, but before we do that, I'm going to go to the end and see this end and how this is exactly like we had before. It will stop reading at this point, and then after that, typically we put stuff like this. So I'm going to put a restart function in here. I did save this, I hope. And now I'm going to do, I don't really need the debug needs package, but I'm going to just do needs package. It gives an error. Okay. That's because where's the error? I come over here. In Emacs, you can click on it. In VS Code, I think you can click on it. And I don't know how to do this in Jupyter at all yet. So, but anyway, so you do that. And the trouble is this doc node here. Okay, first of all, this is like overwhelming. This is a template, so it has all the possibilities in it. And you need almost none of these. Okay, so we're going to, but right for the moment, we're going to talk about documentation later, but right now we're just going to remove the word doc from these things. So it's just like before, it gives us a string in the middle, and just as a string, it will not sign or do anything with it. Okay, so I'm going to do that, and I'm going to try it again. I'm going to do needs package, and it loaded it. Okay, check, we'll run the test. There's one test here that does absolutely nothing. These are all comments. Okay. I can also install the package once I have documentation and view the help of the package. So this is the kind of thing. So what the idea of a package, in case you don't know, is you want to put your code, even if it's on your own project that no one else is going to use, you put it here, and you can put tests in to make sure that some basic things about it work, and you can put documentation in for it, and you actually implement the function. And then when you do the install package or and the test check of the package, it will run all those, it will make the documentation for yourself, for your package, and it will do the tests. Okay. So first thing I would do in this is I would put a date in. So this is 31st of March. You can do it in any form. It's kind of free formatting, 2025. Okay, here it's going to be the Mikester. Okay. And auxiliary files is false. It's just going to be one file package. If you sometimes you can have a package with the name, package name.m2, and then next to it you have a whole directory called package name, and you can put stuff in it. But for the moment, one package is what most packages are, unless they're really big. Now this export list is going to be a list of strings that are the symbols that you are going to want people to use. So why don't we call this oscillator ideal, okay? And we're going to have a graph. By the way, we're going to have to add some stuff to this, but the section is this new package gives you a bunch of information about the package, okay? Like the version, I don't think 0.1 is, we want, actually what one person did for their package, and it was actually not a Macaulay 2 thing, it was it was another thing. They had version 3, version 3.1, version 3.14. And after a while, it gets a little out of hand. So I don't recommend that. Okay. Although it was increasing in number at least. Okay. So now what we have is the code section. You can get rid of this is just a comment. There are two types of comments in Macaulay 2, -- for a single line, and then this thing will be a whole block comment. And documentation section, this is what we took the word doc out of for those things. Actually, we might need to close that door. Thanks. And then you can put tests in. You can put tests in anywhere, but this is kind of a nice thing to put it somewhere. So what we're going to do is we're going to do this oscillator ideal thing. But we need graph. We need to be able to make graphs. So yes, sure. Where did I find it? I inside of Macaulay 2, I ran this.
Oh, okay.
Okay. And then I copied and pasted it into the file. And you could dump that into a file directly, but I just did it this way. So if your package uses other packages, you have to tell it, you have to say that. And so the way to do that is it's called package imports, or I'm going to call it exports. There's two things. This one, if I give it, I'm going to give it a list of package names. And the ones I'm going to give it are naughty graphs. Remember, we already came across, not body graphs. That would be interesting. Naughty graphs and the graphs package itself. Although maybe naughty graphs already uses graphs, I can't remember. If I do needs package of naughty graphs over here, and if I type graphs, what is it? And if I do load package of graphs, it'll give me an error if I've already loaded it. Yeah, it gave me an error. Good. So I'm going to restart. And what I'm going to do is I'm putting naughty graphs. I don't think I need to put graphs in, but I'm going to put it in anyway. Anytime you use something from it, it's a good process. This is useful for a number of things, but including so that you can tell what packages have been used by something, but it will not give it to you if you don't do that. Okay. And now I'm going to write a function called oscillator ideal. I guess I'll do it here. I'm going to make it a method. Okay. Actually, I want to make an example too. So I got to show you how this works. So maybe, in fact, what we'll do is we're going to do our own generate graphs. Okay? And we're going to give it, and generate graphs. Actually, I don't want to call it generate graphs. I'm just going to call it generate. Actually, is generate used for anything? No, good. So generate of ideal, I'm sorry, is equal to a method. Yeah, probably. So this is a comment. I would oftentimes just get rid of that, but it's also reasonable to keep it in. And now I'm going to generate of ZZ. You know, I probably don't need this because once I load this, I have the function generate graphs automatically. I think I'm going to leave it out. Okay. Let's actually do that. Needs package of naughty graphs. Okay. And now if I do generate graphs, is that there? It is. It's a method function. I could do help of it, and it will tell me how to use it. Okay. And it will give me all these weird strings. So actually, maybe we do want generate because we need to get these ideals somehow or another. I'm just going to do it this way. Okay. And I'm going to, right here, I'm going to make one of our examples, and we'll put it down in the test section in a second. Okay. So what I'm going to do is I'm going to do needs package of my package. Okay. And I'm just going to do that, right? I'm going to do a restart in this code. And I'm going to do a needs package. It loaded it. Now, though, with these package exports, I can use these things. So I'm going to call generate graphs. And I give it an integer. And these are going to be, I'm going to call it strs for strings because it gives it to you in a really weird way. I'm going to give it 5 vertices. And this is what each graph, these little symbols are telling you what graph it is. Okay, and it's in some very encoded form, very fast to construct. We can construct all the graphs of size 10 in not such a long amount of time. And these are up to isomorphism. So it's actually really great. It gives you all of them up to isomorphism. So anyway, that's this thing. And now I want to do strs slash string to graph. Okay, remember a list, strs is a list of those strings, slash applies that to each one. So this is going to be a list of graphs. Okay, so I'm going to run this line. Both these functions generate graphs. I think string to graph is also in naughty graphs. Okay, so if I do this one, I get these lists of graphs. Now these lists of graphs here, let's choose the first. The first one is very boring. Actually, this is really boring. We don't want this one. This is the graph of that has no edges. Okay. This one down here has 0 is connected to 3 and 4. These are undirected graphs. 1 is connected to 4, 2 is connected to 4, and so on. Okay. So that's that and we're going to want to call oscillator ideal on a graph. And we'll do maybe I'll make a graph. I'll do G is equal to G's underscore 10. I just picked one. 2 is not connected to anything else though. So that's actually, I should have changed to generate graphs that are connected. So I can do that, you know. I can do connected gets true, I think. Let's see if that works. Nope. Is connected? Wait, I have to do options of generate graphs. You know, you can also look at the documentation. So only connected, that's what it is, okay? Only connected. So this will give me connected graphs, and that gives me a bunch of these graphs. And now I take the 10th one on the list, okay? And now I want to be able to do this line here, oscillator ideal of G. So that will create a ring, and then it will actually maybe we give it a ring. We have to actually make the oscillator ideal first. So we don't need this generate code here anymore. Okay. So we're going to do this thing and we're going to call oscillator ideal and it's going to take an ideal. No, it's going to take a graph. Okay. And it's going to take G and it's going to return, actually, it's going to return an ideal. And the ideal I want to do is the ones without the x squared plus y squared minus 1s, just the other equations. Now, if you remember how it works, it's the following. So first we need a ring. I'm going to do r colon equal, I'm going to do x is going to be, maybe I didn't want to do this. I'm going to change this up on it a little bit. You have to give it a symbol. Sorry about that. And x, and then we're going to index off of x. No, we're not. That's too hard. Sorry. We're going to just do it in here. Let's see. How do I want to do this? So this is get symbol of x, and y is get symbol of y. I can't, I will explain later why I want to do that. But I'm just, at the moment, I'm going to make a new ring. It's going to be Q, a join, X, we need the number of vertices. So how do I get the number of vertices of a graph? If I do vertices of G, it gives them to me in some weirdo order. But if I do number of that, I get the number of vertices. So N is going to be number of vertices of G. Okay? By the way, I can do edges of G as well. And I get all those sets. I think we've seen that before. Okay. So here I'm going to take variables x underscore. Let's do x underscore 0 dot x underscore n minus 1. Actually, I think I can do y underscore this, and it will do x's and y's up to that amount. That'll be our ring. And now I want to do, for every vertex, I want to create a polynomial in these variables. Okay. So for x, for v in, let's do sort. Actually, if I sort the vertices of G, is it a little better? Yeah. So I'm going to sort for v in sort vertices of G. I'm going to list the following thing. Each one is going to be a polynomial, and then I'm going to just do ideal. Okay. So what is it for the vth one? What do I need? Remember what it was? I needed a 2x2 minor of so I need the sum of all of the, I need the neighbors. So how do I get neighbors? Hopefully there's a function called neighbors. And how does it work? If I do help of that, what do I get? Neighbors of the graph, comma, a vertex. Okay. So if I do neighbors of G comma 0, what do I get? I get a set. Bleh. So I'm going to do neighbors of G comma V, and I'm going to do two lists of that, and I'm going to sort it just to keep it clean. Okay.
Why is set bad?
Because I want to do a loop over it, and I can't loop over the. If I do for y in O16 list print y, it expects a list. Okay. So one could put that in, but it's not.
Yeah.
Yeah. So the reason that's not quite done here is because things in sets don't have to be sortable. So you have to be kind of careful if you're writing general code. I mean, here it doesn't matter a whole lot. So this is going to be NBD. That's the neighbors of that. Okay. So if I just run this one line, what do I get? Whoops. If I come over here and I do 0 here, and I get rid of that, let's just do this. It just chooses it in what order it is in the hash table. So it doesn't try to sort it. Well, actually, maybe it does. No, 4,2. Okay, so sorting it is probably what you want, but again, it doesn't probably matter here. Okay, so so anyway, so this is this thing. NBD is sort of that, and now what I want is I'm going to call it X. So how about FX? And this is going to be sum of for I in NBD list I don't think I can do this, unfortunately. Let's see if it works. Okay, this X sub I might not realize that it's in this ring. It might just think it's an index variable, but we're going to try it. Okay, and then at the moment this function is just we're going to just return fx at the moment, and then we'll take the ideal of all these things, and then we'll fix it. So the way we can do this is we're going to take our example here. I'm going to move it out of here and put it down below here where I can see it.
So sometimes you use the slash to do function application, and sometimes you fix.
So wait, sorry. So sometimes I use for this, list this, and sometimes I use slash.
Like it and sort neighbors. So say neighbors slash to this slash sort.
You could do neighbors of G comma V, then slash to list. Actually, it would be slash to list. You would probably prefer to do it this way. That's if you're piping lots of things through. And here you're not. You're just calling this function on the whole thing.
Doing neighbors slash to list would be saying apply to list everything in the list.
Everything in a list. And
this is
but
looking
but
for
neighbors
all
is
of
not a list. It's a set of things. So that's a little different. So here, what I want to try to do now, we're going to get an error here, I think. No method found. So here's the error. First error. What's going on? No method found for applying oscillator ideal to something of type graph.
Have you run the oscillator ideal?
Probably not. Actually, I did do restart and needs package. Oscillator ideal is here. Oscillator ideal is here. It takes a graph. I'm spelling it right. I'm calling it on a graph.
Doesn't need documentation, right?
No, not yet. I spelled that right? Oscillator ideal. Do I have I could have some, and that does end there. I don't think that would be very weird if that mattered, what order it came in. But we are, shoot, that's actually interesting. Maybe
What did
we,
you change, sorry?
I put the graphs after, that is kind of a bug. It's supposed to, it shouldn't really matter what order they're in, but it did. Naughty graphs already, it probably calls graphs. Actually, I'm not sure what's going on, but this X2 and X4 is not, it does not like it. So here's what we have to do. This is actually something important. Variable names in Macaulay 2, it's actually after 1 now. I think we're going to be doing this next time, but this actually is what you want to do is you do this print template. What? You do this package template, you fill out, you have to do the headline, fill out the stuff. Oftentimes I look at previous ones to see what is there to know. There's other things that one wants to put in too that aren't here that we'll have to explain. And then you want to add documentation, and that we'll talk, that's actually a little bit longer. I think we should talk about that next time. But adding a test is good. So let me show you how to add a test. Okay, I'll get rid of those things. And this I would probably replace. I really want to test whether 1 + 1 is equal to 2. Okay, really important to test that. So I'm going to do that, and I just put an assert here. Assert is a programming assert, which says I tell you that this should be true, and then when Macaulay 2 runs it, it will say, is it true? And it will do that. So what you can do is you do this. I'm going to actually fix the, I'm going to get rid of, I'm going to actually do that for the moment. I'm going to comment out that because I have to figure out what's wrong with that.
That's good stuff. And if you load the package for you, sometimes it gives you an error.
If you load what?
Package, one is already called the other.
Yeah, that's right.
Something else that gives you error.
Yeah, that's right. So, but if you put it in the export list, it shouldn't reload it, but it's obviously doing something. So I have to look at that. Okay. So here's needs package, and now I can do check, and it checked it. Okay. So in fact, what if I really thought, and in my heart of hearts, I know that 1 + 1 is equal to 3. I can come down here, I need package, and I check it, and I get an error. And I can say, oh crap, look at this. It's all these, and on the Mac, it's especially bad. It puts it into some really horrendous location. But if I come in Emacs and also in VS Code, you can go to that line and it will show you what the problem is. It goes to it. Here, let me make it larger. It will go to it, and then it shows you that the error, the assertion failed, is on this line. So you can go right to it. And so you can check all your tests, and it will, if it worked fine, it will say, you know, it will end, and it'll say, it won't say that there's an error, and everything's good. So it's really good to do both documentation and tests, and for all of your little functions too, you know, so that you make sure that what you do want to do is you don't want to write 10 functions and then test it once at that point. You should, when you write a function, just give it a simple input and output that does it. And also, if it turns out that your function is not a useful one, or it's a pain to use, you're going to be the first one to find out that it's a pain to use. And so you can change the interface of it. You can say, oh, no, I don't really want to give that much detail. If you have, for instance, if you write a function with 5 or 6 arguments, that's almost always hard to use. So
Poetry doesn't let you do that.
it doesn't let you do methods with that many things, but it will let you do functions with that many things.
What's
So
the maximum for, what's for method?
4.
That's hard coded.
Yeah, that's hard coded. That's hard coded. And that would be kind of a pain to change. Okay, so anyway, that's all for now. Sorry for going over on that.